Okay, so I have gotten bored today and I'm trying the physics admission test from October 2023. And I probably should warn everyone watching that I don't know physics too well. There are going to be some questions that I'm going to do horribly wrong. So please just watch this video and try not to get mad if I do something wrong, please. Thank you. Well, yeah. So I guess I'll start. And it says you can take the gravitational field strength to be 10. That's wonderful. Okay. All right. Oh, shoot. Question 1. What speed does a bull elephant of mass 4,900 kilograms have to move at to have the same kinetic energy as a cyclist of mass 100 kilograms moving at 30 kilometers per hour? So we can start this off by defining kinetic energy, which is 1/2 mv squared. And for that fact, we should probably say that the kinetic energy of the bull, the mass of the bull, the velocity of the bull. And we said that we have to have the same kinetic energy as the cyclist, meaning kinetic energy of the bull is equal to kinetic energy of the cyclist. And kinetic energy of the cyclist would be 1/2 mass of the cyclist times the velocity of the cyclist squared. Oops. But fun, you'll notice that they gave us the speed of the, or velocity, I suppose, of the cyclist in kilometers per hour, and all the answer choices are in meters per second, meaning we have to do a bit of a conversion. So if you want to go from kilometers per hour to meters per second, you have to divide by a factor of 3.6 because you multiply by 1,000 to go from kilometers to meters, and you divide by 3,600 to go from hours to seconds. So we have that the guy's velocity is 30 kilometers per hour. So if we do 30 over 3.6, we'll get that his velocity is 25. Oh my God, that doesn't look like a 25. 25 over 3 meters per second. Sorry. So now we have the guy's velocity, and actually we have everything we need to solve for the kinetic energy of the cyclist. So the kinetic energy of the cyclist is going to be 1/2 times his mass, which is 100 kilograms, which is kind of interesting. And then his velocity squared. And this time it's in SI units. Have fun. So you have 25 over 3 squared. And if we multiply this back out, and I'm using a calculator in my hand because I don't want to use the nasty one provided online. So let's see, we'll have 50 multiplied by 25 squared divided by 9, which is approximately 3472.2 joules of energy. But we can notice that since the kinetic energy of the cyclist and the kinetic energy of the bull have to be the same, we can just plug this in right there. Which means if we solve for the velocity of the bull, we'll say that the velocity of the bull is the square root of 2 times the kinetic energy of the bull, or in this case, technically the cyclist, but they're the same, divided by the mass of the bull, not of whatever that is. Well, just pretend that's a b. And if I plug this in, so I multiply by 2, I divide by its mass, which is 4,900 kilograms. And then I take the square root. That gives us an answer of 25 over 21 meters per second. And that in decimal is about 1.19, meaning that our answer for this question is B. Yay, how fun. Next question. A seed packet contains 100 seeds. When planted, 75 will successfully become plants, but of these, only a third will have flowers, and of these, only a fifth will have fruit. How many seeds produce fruit? So in this problem, it gives us that there's 100 seeds, but it doesn't really matter because they say that only 75 will successfully become plants, so the other 25 don't matter. And now it says only a third will have flowers. So to find the number of seeds that have flowers, we multiply it by a third. And then it says a fifth of the ones that have flowers will produce fruit, meaning we have to divide by 5 again to get the number of fruit, or rather seeds that produce fruit. And so if you multiply 3 times 5, that's 15. So you're dividing 75 by 15. 75 over 15 is 5, meaning our answer is A. Isn't that fun? Okie dokie. Next problem. Oh, hurts. Two black holes orbit each other and emit gravitational waves arising from the periodic nature of the orbit. The orbital separation is around 10 kilometers. The relative speeds of the black holes are close to the light of speed, and gravitational waves travel at the speed of light. Which of the following would best describe the frequency of the emitted radiation? So I will start this off by saying I don't know much about waves, and this is one of the aspects of physics that I suck at, but it does say that they're around 10 kilometers away. So I suppose we can start by converting 10 kilometers. That's not a K, but pretend it is. To 10 to the 4 meters. And now it's asking for the frequency, and it mentions the speed of light. So I'm going to use the only formula that I know, which is c, the speed of light, is equal to lambda times nu, where lambda is the wavelength and nu is the frequency. And if we solve that for nu, this is going to be c over lambda, which I pray is correct. And c is about 3 times 10 to the 8. And lambda in this case, I'm going to pretend it is 10 to the 4 because I don't know what else to put here. And that gives us an answer of 3 times 10 to the 4, which puts the order of magnitude at 10 to the 4. So I'm going to pretend the answer is C. Once again, that was probably wrong, so please don't blame me. Well, I suppose you can, but it won't make a difference. All right, next question. What is the next number in the sequence 1/5, 3/25, 7/25, 3/25, and 31 over 3,125? Okay, well, so one thing I suppose we can notice is at the bottom, it seems to have a trend of following powers of 5, because 5 to the 1 is 5, 5 to the 2 is 25, 5 to the 3 is 125. But this breaks here because 5 to the 4 is not 125, but suspiciously, 5 to the 5 is indeed 3,125. So what we can do is we can pretend to try and make this sequence fit our liking and say that it's 3/25, 7 over 1/25. And then since this is off by a factor of 5, from 5 to the 4, we can just multiply by 5 over 5, giving us 3 times 5 over 5 to the 4, which is, what is it, 625. And the last term obviously would be, was that 31 over 3125. That is the ugliest 3 I've ever written. Okay. So now we have a trend that each one seems to multiply by at least a factor of 1/5. So that suggests that this is probably a geometric progression of some sort. And now we can see that the numbers on the top are 1, 3, 7, and 3 times 5 is 15, and the last one is 31. So on the topic of powers, it's fairly simple or interesting, I'll say, to notice that all of these numbers are fairly close to a power of 2. And actually, they're all a power of 2 minus 1, because 1 plus 1 is 2, which is 2 to the 1. 3 plus 1 is 4, which is 2 to the 2. 7 plus 1 is 8, which is 2 to the 3. 15 plus 1 is 16, which is 2 to the 4. And 31 plus 1 is 32, which is 2 to the 5. So we've also somewhat established a power, or I mean a rule for what the numerator follows. So for the nth term, it seems to follow that the term on the top is 2 to the n minus 1. And the term on the bottom is 5 to the n. And we can see that this works indeed, because 2 to the 1 minus 1 over 5 to the 1 is 1/5. 2 to the 2 minus 1 over 5 to the 2 is 3/25, and etc. for the rest. So now we want to find the next term. So since we already have 1, 2, 3, 4, 5 terms, we need to find the sixth term. So we want 2 to the 6 minus 1 over 5 to the 6. Now, I don't want to calculate 5 to the 6, but I can see that I know what 2 to the 6 is. 2 to the 6 is 64. 64 minus 1 is 63. And since 63 is co-prime to whatever this is, we can say that the answer choice with 63 in the numerator is going to be our answer. So here we have that E is the only one with 63 in the numerator. And this is also probably the correct power of 5, considering that 3 times 5 is indeed 15. So wonderful. Our answer for number 4 is E. Okie dokie, next problem. What is this? Consider the pulley system in the diagram containing 4 wheels. If you pull the free end a distance y, how far will m rise by? What? Okay, so I'm not going to do this one because I just don't know what this is asking, and I'm going to come back to it later, because why not? And next question. 6. Consider f of x is equal to x squared. You want to transform the function so that you get a new function g of x stretched by a vertical scale factor of 2 with a line of symmetry about x equals 1, and which is never positive. G of x would be equal to which of the following functions? So this is pretty, not the hardest, but it's, I suppose, moderately interesting. You could see, so f of x is a x squared, which means it's a quadratic. And it says that we have 3 conditions to follow. So there has to be a vertical scale factor of 2, sorry, a line of symmetry about x equals 1, and it's never positive. So the easiest one to start off with is this never positive. And this condition really doesn't help us because, as we see, all of these are negative, and since f of x is already a positive, multiplying a negative by a positive gives you a negative, so this condition doesn't really help us with anything. The next condition that we can check is, I suppose, the line of symmetry about x equals 1. So f of x has a line of symmetry about x equals 0, which also happens to be its only root. So if you wanted to move it to x equals 1, that means you would have to translate it to the right by 1 unit. And how you express that is you would say f of x minus 1 instead of f of x plus 1. Because when you want x minus or x equals 1 to equal 0, you would get that x minus 1 equals 0. And so if you apply f to both sides, that would replicate the same effect for f of 0 here, which is where its line of symmetry is. So we can eliminate any of them that don't have x minus 1 in the argument, which is C and D, and technically not E, because we can see that there is 2 times x minus 1 here. 2 times x minus 1. That was ugly, but you're going to pretend you can see that. And the last one condition is that it's a vertical scale factor of 2. So we can already eliminate B now, considering that there's no 2 anywhere to be seen. And so now we're between A and E. So A has a 2 on the outside of the function, whereas E has a function on the 2 on the inside of the function. So from this condition, we can see that g of x, if it's scaled by a factor of 2, it's going to be proportional to 2x squared. And if we have a 2 inside the argument, such as with E, if we even see what f of 2x is, that's equal to 2x squared, which is actually equal to, 4x squared. And that actually scales it by a factor of 4 rather than 2. So we can actually already cross E out, and we see that our answer is A. Isn't that fun? Okie dokie. I don't know why that was here though. I thought that was the physics test, but I guess that can be counted. Okay. If y equals 2 plus x over 2 quantity to the fourth, which of the following is dy dx? So I kind of don't want to take the derivative of this, so I'm going to do a little scammy method. In the expansion of this quantity here, the largest term would be x to the 2 to the power of 4, which is x to the 4 over 2 to the 4. 2 to the 4 is actually 16, so we can just simplify that. And since the derivative is a linear operator, we can take the derivative of each term individually, meaning that the derivative of this term here should show up in the final expression. So the derivative of this, if we take it, would be you bring the 4 down, and you can actually cancel it with the 16. So you would have x to the 3 over 4. So we can actually already start crossing stuff out. Option A has x to the third over 4, so we can't actually cross that out. Option B has x to the third over 8 as its highest term, which means we can cross it out since this has to be the highest order term in the derivative of y. Same goes with C because it's x to the 3 over 2 instead of 4. And we can't cross out D because it does have x to the 3 over 4. But we can also cross out E based on the fact that x to the 3 over 8 is not equal to x to the 3 over 4. And what we can do now is we can use the fancy binomial expansion thing to find the coefficients for the terms that we will look at. And since this is pretty simple to do, I guess I'll just look at the linear term because the linear term here is 4 and the linear term here is 16. And when I say linear, I mean the derivative of the linear term in the original one. So technically I should say the constant term. So by the expansion, it will be, let's see, you would have 2 to the, what's the next? What's after 1? It's 2 times x over 2 to the 2, since 2 plus 2 is 4. And this would be the third term actually, right? Because you start with 2 to the 1, and you move to 2 to the 2. Let's see. You start with, sorry. You start with 2 to the 4 here, and you go to 2 to the 3, and you go 2 to the 2. So it's actually going to be multiplied by 6, which means we find this number. And coincidentally, 2 to the 2 and 1/2 to the 2 cancel out because they're inverses, reciprocals, I should say, which means that we will have 6 times x to the 2 as the term in y, meaning if we apply the derivative operator, it'll be 12x, which means we search for the linear term of 12x. And here, that's actually that, which means our answer is D. Yay! Okie dokie. Oops, I forgot to clear it. Oh no. All resistors in the circuit below have the same value. If an ammeter is placed in the circuit in turn at points A through E, which of the following sets of points will give the same reading? So I'm not very knowledgeable in circuits, so I'm just gonna use what I know. So I know that V equals IR is, I believe, Ohm's law. I'm hoping it's Ohm's law. And I hope it applies here because otherwise I don't know what to do. Which would mean that if we wanted to isolate the value measured here, we'd have to rearrange these terms. So it says an ammeter, which I assume is for measuring amperes. So we want I, which is equal to V over R. Now I'm going to hope that V can remain constant and the resistance is all that adds because I don't know how else to do it. So in my bad way of solving it, we have here first two resistors in parallel. Actually, this is right before it. So I don't know what, there should be no resistance here. I'm just going to pretend that the resistance is 0 at A because I don't know what else to do. Now to calculate the resistance at B, I'm going to assume it works like you used the previous ones. So you have to do 1 over R plus 1 over R and then 1 over that, which means the resistance at B will be R2, R over 2. I don't know if that helps with anything, but I guess I'll find out. Is this actually how it's supposed to work? Because if that's the case, then C and D should have the same resistance considering they're here. But that wouldn't make sense, would it? Ammeter is placed in the circuit in turn. Oh, wait a minute. I don't know which direction the current flows. I might be doing this wrong. You know what? I'm going to not go with it. Actually, you know what? I'll solve the mechanics questions first, and then I'll come back to the nasty stuff. How about that? Or whatever this is too, I suppose. Okie dokie. So if dy dx is equal to x squared plus 1 over x cubed, and y equals 0 when x equals 1, what is the integral from 1 to 3 of y with respect to x? So we're given a differential equation and an initial condition here. That I meant to underline that actually. So I was saying we have an initial condition, which means that y of 1 is equal to 0 since it says when x is 1 and not when y is 1. So y of 1 is equal to 0. So then we have that if we rearrange this differential equation here, we get that dy is equal to x squared plus 1 over x cubed dx, which means if we integrate both sides, that integration sign, we'll get that y is equal to some constant c plus x cubed over 3. And this is x to the negative 3, so you have to add 1 to the power, which is negative 2, and divide by it, which means minus 1 over 2x squared. And yeah, that's actually it, because the constant term, we can just consider the constant term compressed into this c. And it says that y is 0 when x is equal to 1. So that we have 0 is equal to c plus 1 over 3 minus 1 half. And this here is actually equal to, I should say, negative 1/6, meaning that c is equal to 1/6. C is equal to 1/6. Okie dokie. And then now we have to integrate it from 1 to 3. All right. So I'm going to clear this. Now that we have that y is equal to 1/6 plus x cubed over 3 minus 1 over 2 times x squared. We have to integrate it from 1 to dx. Probably put a dx here as well. Okay, it's kind of, I mean, it's not really that hard, I guess. So we'll have x over 6, plus, since that's supposed to be an x cubed, it's going to be plus x to the 4th over 12, and have fun. Okay, x to the negative 2 over 2, add 1 is negative 1, and you divide it by negative 1, which means it's going to be plus 1 over 2x. Yes. And this is going to be evaluated from 3 to 1. So at 3, we have that it's 1/2 plus 81 over 12 plus 1/6 minus 1/6 plus 1/12 these plus 1/2. So if you'll notice, this 1/2 actually cancels out with this negative 1/2, and this 1/6 cancels out with this negative 1/6, which leaves us 81 over 12 minus 1 over 12, which is 80 over 12, which if you divide both the top and bottom by 4, that's equal to 20 over 3, meaning our answer is C. Yay. That's actually surprisingly a bit longer. Although then again, I haven't done too well on this, so I can't say much. Okie dokie, next problem. A particle of mass m traveling freely at an initial speed v can be stopped in, oops, my bad, can be stopped in a distance d by a constant retarding force F. What magnitude of force applied in a direction perpendicular to the motion would be needed to change the trajectory of the same particle at the same speed v into a circular arc of radius d? So I'm going to do a kinematics approach. So if we want to find the acceleration or the force even, we note that Vf squared is equal to V naught squared plus 2 times acceleration times the distance. And this acceleration, we don't know what its sign is right now, so there's that, yes. And yeah, okay, so if we solve, we know that Vf, it says it can be stopped, meaning that Vf is 0, and that's equal to V naught, which is V squared, and the acceleration is 2f over m by Newton's second law, which is F equals ma, and d is just d. Meaning, if we rearrange this for, what are we trying to find? F, I believe, yes. F is equal to, so you subtract V squared, you have negative V squared, and you have a factor of 2D over M, which means you have to multiply by M and divide by 2D. So this is the magnitude of the force, if you're stopping it when it's going in a linear manner. And now it says what magnitude of force applied in a direction perpendicular to the motion would be needed to change the trajectory of the same particle into a circular arc of radius d. Radius d is important. So that basically means we can apply the logic of centripetal motion. So that basically means that we need to calculate what would be mv squared over r, and that would be the force. And so we have m is m, v squared is, oh, I suppose we were supposed to rearrange. I mean that if we do have v squared, actually we can probably just leave it there. Let's see, v squared and over r is d. So if we notice something, we'll see that if you multiply this by negative 1/2, you'll actually get this, which means that the force centripetal is actually also equal to negative 1/2 of the force that we had, which I guess I'll just call it linear. But we want the magnitude, which means the magnitude of F centripetal is just equal to the F linear over 2. That is horrible too. That's supposed to say 2. So it'll be A, right? Yes. Yes, the F centripetal will be F linear over 2. Nope, that's not right. That is not right. That is very much not right. I misread my own writing. It's not actually right because to go from FL to go to FC, you actually need to multiply by -2. So it's actually going to be -2 FL, meaning the magnitude is not FL over 2, but it's actually 2 times FL. And that makes a lot more sense, meaning the answer is actually E. So not that. It's not that. Okie dokie. That was a nice question, I suppose. What is another math one. What is the integer m such that the sum from 1 to m of 3 plus 2n is equal to 140? Okay, well, if you know stuff about arithmetic progressions, this is pretty simple. So first we can use a property that says the sum from n is, if I can write it, 3 plus 2n. That sum is actually going to be, you can split the sum basically. So it's going to be the sum from 2m from 1 of 3 plus the sum of n from 1 to m of 2n. And I suppose this is just a matter of remembering formulas. So for the first part, you will basically see that if you add from 1 to m, for example, let's take m is 2, which means you'll have n equals 1, so you'll add 3, and n equals 2, so you'll add 3 more, you'll have 2 times 3. So this basically means you'll add 3m times, which means this will just simplify to 3m. And for this one, there's, I suppose, a formula that says the sum for something going from 1 to m of n is n times n plus 1 over 2. And since this is multiplied by 2, you can basically just multiply this by 2. And you'll get that this is actually then just equal to m times m plus 1. And this you also know is equal to 140. And this actually gives you a quadratic equation. So you have that m squared And since you have plus 1m plus 3m, you have m squared plus 4m minus 140 equals 0. Now I would like to try and factor this. Let's see. 140 is equal to 14 times 10. So that's actually very convenient that we saw that. So you can actually just factor it as such. You get that m plus 14 times m minus 10 is equal to 0. And the trick is try and find the two closest factors because the difference isn't very big. And so if we solve each of these, we'll get that m is negative 14 or m equals 10. So we don't want to be summing from 1 to a negative number because, yeah, no, it's just no. And also, it's also not one of the options. So therefore, our answer is actually this, which is m equals 10, meaning our answer is C. Okie dokie. All right. Oh God, another electricity one. That's not going to end well. How about I come back to it? Because, yeah. Okay, you use some measuring scales to discover the following relationships between masses of apples, bananas, and carrots. And you have these equations. Let's say 2ma plus 3mb plus 4mc is equal to 4ma plus 3mb plus 3mc, and ma plus 4mb plus mc is equal to 8mb. And it's asking us to find all combinations of apples and or bananas that have the same mass as 5 carrots. Note that only whole numbers of apples and bananas are allowed. Oh, this is fun. It reminds me of the nursery rhyme. Okay, so I suppose we can start working from the first equation. And if we look at all the terms, we'll actually notice that there's a term of 3mb on both sides. So we can actually just cancel that. And that leaves us with this thing that says 2ma plus 4mc is 4ma plus 3mc, right? So we write that here. I don't want to write m so many times, so I'm just going to write 2a. The 2a plus 4c is equal to 4a plus 3c. And if you notice, there's a 4 here and a 3 here. So meaning we can actually isolate c already. We can say that c, if we subtract 3c from both sides and subtract 2a from both sides, is equal to 2a. So we have already a relation that we can set up, but let's go to the next one as well. And that says that ma plus 4mb plus mc is equal to 8mb. So we can actually cancel these terms here because there's mb's on both sides, which leaves us with 8 minus 4. Well, I'll just write 4. It leaves us with 4b on the right. So then we get this equation that says a plus c equals to 4b. But since we have this equation right here, we can say that, so 2a is equal to c, which means this is 2a plus a, which is 3a. So we can say that 3a is equal to 4b. And that's another relation. And now we want to find all combinations of apples and or bananas that have the mass of 5 carrots. So we can see if we multiply this equation on both sides by 5, that we'll have 5 carrots is equal to 10 apples. And I suppose you can say that 10 apples can be split up into this. So let's start with all the combinations. So if we have only apples, then we'll have that 10 apples is one combination since it makes 5 carrots, which is what we're looking for. And if we have, let's say, 9 apples, that would mean we actually can't do that because the mass of a banana is 3/4 of the mass of an apple, which means we need to subtract apple masses in groups of 3 to get any B's involved there. Which means that we can also then look at the first subtraction of 3. We'll have 7a plus, 4b, because 3 apples is 4 bananas. So you have 7a plus 4b. And then if we remove 3 more, we'll have 4a plus 8b. And if we remove 3 more, we'll just have that a plus 12b. And these are all equal to 5 carat masses. Now, there is no solution in which you can have only bananas making up the mass of 5 carats, since the problem specifically says that only whole numbers of apples and bananas are allowed. So this actually means that these 4 are the only combinations that are possible for this problem. So that's fun. Okie dokie. We're all drawings. How long have I been? Who knows? Okay, another math one. If 2 to the power of x plus y is equal to 16 and x times y equals 2, find x and y. Okay, well, so if we see that we can see something here called exponents, I suppose. So 16 is actually a power of 2, so we have that 16 is actually equal to 2 to the 4, which simplifies our equations if we equate exponents, that x to the x plus 2y is equal to, x plus 2y is equal to 4. And here we have that x times y is equal to 2, which means we can actually say that, for example, x is just equal to 2 over y, which would give us 2 over y, should say that that's a y, plus 2y equals 4. If we divide both sides, we'll get, divide both sides by 2, I should specify. We'll get that y plus 1 over y is equal to 2. And we want to find x and y. This is basically, so 1 over y, this is x over 2. So we have x over 2. We could have gotten this from the original equation, I suppose, but it doesn't matter. So we'll multiply y to both sides, and we'll get that 2y, if we look at that side, is equal to y squared plus 1. And if we do this, we'll get that y squared minus 2y plus 1 equals 0. And if you notice something, this is actually a perfect square of y minus 1. And that's equal to 0, meaning that y is equal to 1. And that means that x is equal to 2 divided by y, which means x is thus equal to 2. So we have that x is 2 and y is 1. And we can actually verify this in the original equation as well, because we'll see that 2 times 1 is 2, and 2 plus 2 is 4, and that is indeed what we get if we plug the values of x and y into this equation. So that was it. That was problem 6. No, it was problem 14, my bad. Okay, next problem. Oh no. Okay, this one might be a little hard for me. Okie dokie. A ball of mass m sits in equilibrium on top of a set of 3 identical springs of spring constant k, as in the diagram. You can assume that the springs are stiff and the ball is light. The ball is pressed down by a distance x and then released. Assuming that 90% of the stored energy is transferred to the ball, how high will the ball go above its point of release? So this is going to involve conservation of energy. K, M, K, X, and G, where G is the acceleration. If we consider this to be y equals 0, then we have no gravitational energy to consider initially. Actually, no, that's not nice. We'll just consider that this is y equals x, because when it's pushed down by x, then it'll have no gravitational energy. So if we consider this y equals x, how do we go about this? So there's two springs here that both have spring constant k. And if you consider this as a system, if you displace this board by an amount called, I don't know, dx, both of the springs will have an upward force, and that upward force will be kx from each of them. But since there's two, this board will face an acceleration, or I mean force of 2kx. 2kx. So for the bottom two springs, you can effectively consider it one bigger spring with a spring constant of 2k. And now there is the annoying bit of actually doing the problem. I assume these boards are these even boards? Yes, these are boards. I assume these boards are massless because they're not talked about. Um, hmm. How do I go about this? Let's see. Well, let's consider the upper spring. So on that, the forces that are external, you'll have the force of whatever it is pressing down, and then force of mg. And this will be equal to whatever force is exerted on it. How does this actually work? Actually, I suppose if we can consider the bottom spring a spring of length L, for example, and this is also length L, and this has spring constant 2k, we can probably consider the whole thing as one big spring. So you could probably, I'm going to pretend at least, that you can add the spring constants to get 3k, because that's how it seems to be working to me. Well, I'm going to pretend that this is how I'm going to solve it. So if it's a spring of length L, then the potential energy that'll be gained at the point point 0, that'll be 1/2 kx or I should say 3kx squared, because it'll be one big spring with a spring constant of 3k. At 3kx squared, there's no plus term actually because there's no gravity to consider. And that's going to be equal to, what are we trying to find? How high will the ball go? Which means, suppose mg y, which is going to be the gravitational energy, right? Actually, first we can consider the kinetic energy. 1/2 mv squared. And that's actually all going to be converted into gravitational potential energy, because the ball thing will be launched up and it will stop. The maximum height will be when it stops moving altogether, but it'll have all the gravitational potential energy then. So if we do that, we can actually probably just say not 1, 3/2 kx squared is going to be equal to the change in height. And the change in height is y final minus y initial. So the y final was y, which is the maximum height, and y initial was actually x or negative x. So we will actually have y plus x here. Ew, do I have to do quadratic? Oh, I think I have to do quadratic equation. This is not fun. Okay. Then that you have 3 over 2k x squared minus mg x over, oh wait, no, I don't. What am I yapping about? Oh, no. Let's see. Mg x, yes, divided by mg. Yeah, divided by mg equals y. I should probably say that this is y max. So this is what I'm going to assume is the solution because this is the best that I can do. So let's just look at the logic. Oh no, wait, it's not the solution actually because it's 90% of the stored energy. So there should be a 0.9 here actually times that. Or is there? Actually, 1 minute. I'm going to erase this bottom part. I'm going to erase this bottom and just redo it. It's not much to redo anyways. So, but since it's, I'll say times 10 over 9 because there should be a 9/10 factor on this side and I just multiplied it here. And 9/10 over, or 9/10 times 1.5 will be 2.7. So it's actually going to look like this, 2.7 kx squared over mg minus x. And that should be y max. Yeah, I think that should be it. Okay. This is a long test. This takes a long, I'm kind of bored of it. Well, I suppose it's longer because I have to draw this stuff out. That's what I'm going to tell myself. Okay, in astrophysics, the gene's length, lambda j, is a measure of the size of a cloud of gas in which internal pressure just supports the cloud against collapse against gravity. It depends on the speed of sound, cs, the gravitational constant g, and the mass density of the cloud rho. The dependencies may be expressed in the form lambda sub j is cs to the alpha, g to the beta, times rho to the gamma. What are the values of alpha, beta, and gamma required for lambda j to have the correct units of length? Okay, so basically what I'm going to do is I'm going to say it has 1 unit of length, right? Because it's just long, it's a wavelength. And I'm going to expand each of the other ones, sorry, dimensions out. So CS is the speed of sound, which means it's going to have meters per second to the alpha. G is, oh, those are displeasing looking units. Okay, inverse kilograms, nope. I'm going to start with meters cubed divided by kilograms times seconds squared. And that's all to the beta. And then you have rho, which is the mass density. I'm just going to assume that means, oh, what did I just do? That's not nice. That's going to be kilograms per meter cubed to the power of gamma. Okay, so if we notice something, we'll see that there's units of like kilograms and seconds, which don't show up in the final answer. So we can actually work faster to, work more efficiently, I'll say, to cancel those out. So here we have seconds inverse to the alpha, which basically means negative alpha because it's to the power of -1. You have seconds inverse squared to the beta, which means -2 beta. And that's actually it, because that's the only seconds term, and that has to be equal to 0. And if we can actually change these negatives to pluses, keep a negative out here, I suppose, if you want. And there's also stuff like kilograms now. So you have inverse kilograms, means negative beta, and plus gamma actually, because it's kilograms to the 1, I believe. Yes. And that's equal to 0 as well, because there's no powers of it. And that actually tells us that gamma is equal to beta. And that's very convenient. It's very convenient. And now for the meters. So we have alpha, because there's 1, plus 3 beta, and then -3 gamma equals 1. And we want to find the values of these things. So alpha plus 2 beta, as we see here, is actually 0, which means from here we can take out a factor of alpha plus 2 beta, and we'll be just left with beta, beta minus 3 gamma is equal to 1. But you'll actually see that beta is equal to gamma, which means this is actually just -2 gamma equals 1. And this gives us our answers. So gamma is going to be -1/2. Beta is equal to gamma, so it's also going to be -1/2. And since beta is -1/2, that means alpha plus 2 times -1/2, which means alpha minus 1 equals 0, which means alpha is actually just 1. Let's just check that works. Yes, I think that works. And those are the answers for question 16. Okie dokie. I hope you're allowed to use pen and paper on this actual test. It'd be very displeasing to have to do stuff like this. Okay. A mass M on the end of a rigid rod of negligible mass from a pivot hangs from a pivot point. The pivot point moves horizontally at speed v, and the mass experiences a drag force, f of v, in the direction opposite to its velocity. At speed v, the rod makes a constant angle theta to the vertical. Find an expression for Fv in terms of the angle theta that the pendulum makes to the vertical. Well, if we consider the forces on here, oops, I forgot I have to switch the pen. If you consider the forces on here, you have Fv going that way, a tension going that way, and mg going that way. This actually tells you a lot about what you need to do. So you can basically see that t, if we take this vertical component here, that'll actually cosine since theta is up here and not here. So you'll get that t cos theta is equal to mg, and you'll get t, and since this is cosine, this has to be sine, means that t sine theta is equal to f of v. And if you divide these expressions, you'll get that f of v over mg equals tan theta. Because the factors of t will cancel out and sine over cosine is tangent. So you have that f of v is, this is a very bad way to write it, mg tan theta. Okie dokie. So that's the part A. Sketch theta. Oh, theta as a function of v in the case that f of v is proportional to v. Oh, that's not what I meant to do. In the case that f of v is proportional to v. So that would mean that f of v is equal to some constant a times v, But we also know that it's equal to mg tan theta. And what do we want? We want theta as a function of v. So if we have that AV equals mg tan theta, sorry, I write my t's weird. If we divide by mg and take the arctangent, we'll get that theta is equal to tan inverse of AV over mg. And that we can consider A over mg to be just some scalar. So if we're actually drawing, we are drawing theta as a function of v, right? Yes. So if we have theta here and v here, this will be the arctangent graph. So arctangent, which way does it go? It goes this way, I think. It's going to be something like that. And does it approach a value? Yes. Okay, so arctangent generally approaches pi over 2. So that means AV over, or A over mg has to equal pi over 2. No, that's not right. The limit as v goes to infinity will be, actually it doesn't matter because there's nothing actually modifying it, is there? Yeah, as it goes to infinity, it'll still be asymptotic at pi over 2 because that's just how the arctangent function is. But like the slopes at 0 and everywhere else, those will be different. But yeah, that's basically just it. And I suppose you could also say negative pi over 2. Yeah, that is question 17. Oops. Okay. I might actually not do all of these. They're getting very tiring. Okay, a quartic polynomial function f of x has the following properties. The second derivative of f with respect to x is 0 at only 1 and 3. The first derivative of f is 0 at x equals 2. And f of 0 is 0 and f of 1 is 3. Okay, so we want to, oh, we have to find f of x. Okay. How would I go about this? The second derivative, well, so f prime of x, actually f prime prime of x is going to probably be like a times x minus 1 times x minus 3, right? Because that's what it says here. F prime of x is 0 at x equals negative 2. So that would be the integral, the integral of that, right? So that'll be a times, what is this? X squared minus 4x plus 3. So that'll be x to the third over 3. So that was x squared, and then it was minus 4x. So minus 2x squared and plus 3, which means plus 3x. Then there will probably be like a plus c term because, yeah. And if, or is there actually? Well, let's see, f of 0 means all of this is going to be, no, that's f prime of 0. Yeah, there's going to be some constant, I think. And then f of x, let's just integrate it one more time. So if we integrate a, well, not integrating a, we're integrating this whole thing with respect to dx. Um, hmm. Let's see, this is x, that's supposed to be a 3. It's gonna be x squared over 3 minus 2x. So that would be what, 3x? This is kind of nasty. The derivative, okay, let's see if I can graph this. Maybe that'll be less work. So f of 0 is 0. F of 1 is 3. And at 3, it has a concavity change. And the derivative is 0 at x equals 2. This is 1. This is 3. This is 2. F of 0 is 0. F of 1 is 3, which means it's increasing on this interval. Is it decreasing? Its concavity changes are at 1 and 3. Oh, this is annoying. I'm not, kind of don't want to do this. This is a lot of work. Maybe I shouldn't have done this test. Who cares? But that's right. So, okay, then the derivative is 0 at 2. Oh, I see. I think we're supposed to be able to find how to represent C in terms of A. Oh my God, I think I've been doing this for more than an hour. It's actually so sad. And I still have questions that I haven't done. Let's see. A, oh, f prime of 2 is equal to 0. That's right. So 8/3 minus 8 plus 6 plus C is 0, which means, okay, so this is minus 2. So 2/3 of A. So C is, if you rearrange, so this whole thing evaluates to 2/3. And if you move it to the other side, you get C is negative 2/3 A, which means you can actually say that f prime of x is equal to A times x cubed over 3 minus 2x squared plus 3x minus 2/3. And you can bring that in because it has a factor of A. I should actually say it's not minus 2/3, it's minus 2/3 A. Okay. And there's that. And then you integrate it one more time. Get the f. Oh, this is so nasty. A times you integrate all of that garbage. 12 minus x cubed plus 3 over 2x squared minus, the pen is slipping, minus 2/3 x plus c. I'll just say it like that. That's what it is. And you have that f of 0 is 0. So everything in here would be 0, meaning that's also 0, which means C is actually, or I should say C1 probably. C1 is actually 0, so how fun. We don't have to deal with that. And then I think to find the value of A, we do plug in 1, which is f of 1 equals, what did it say? 3. That's equal to A times, all right, 1. So you have 1/12 minus 1 plus 3 over 2 minus 2 over 3. Isn't that fun? Okay, let's simplify this a little mentally. So minus 1 plus 3/2, that's plus 1/2. 1/2 is 6/12, so that's 7/12. And 7/12 minus 2/3 is the same thing as 7/12 minus 8/12, which is negative 1/12. So this gives us that 3 times negative 12 is equal to A. That actually lets us solve this godforsaken problem, which means that A is negative 36. Whatever. Oh, that's perfect. We have f of x equals negative 36 times this mess. X to the 4 over 12 minus x cubed plus 3 over 2x squared minus 2/3 x. Isn't that fun? Yay, I can be done with this now. Okie dokie. That was actually had to use my brain a little. It's kind of annoying. Okay. On a side note, this is kind of annoying that they put such an easy question after the. Okay, I won't say the last one was very hard, but it was pretty annoying. All right, so we have solve for x basically. So I can notice something here, which is there's e to the power of 2 here and e to the power of 1 here, and they're both x's, of course. So if I just set e to the x equals u, I get that 6u squared plus u, then minus 15 equals 0. I guess I can quadratic formula it, or is there a better way? So this is probably going to be 5 and 3, and then let's see. 5 and 2, and then 3 with 3. So it's probably going to be like 3u something times 2u something, but I think there's going to be a plus, or no, minus 3 here, and a plus. That was a very ugly plus. Does that work? Yes, it does. Plus, what was it? 5. And this gives us two solutions, which is that u is negative 5/3, or that looks like a 5, actually. Yes, there we go. Or u is 3 over 2. Now, we can already throw this solution away because we here see that e to the x is equal to u, and e to the x is always greater than 0. So e to the x is positive, therefore u is also always positive. That's supposed to be a 0. But yeah, which means we can just throw this out, and e to the x, we can substitute it back in. E to the x is 3 over 2, which means x is the natural logarithm of 3 over 2. And I probably should calculate it, but I don't think they'll care too much. But there we go. That was the solution to 19. Another one I don't know how to do. Let's not do that one right now. Okay. And 21. This one, maybe I can do it. Okie dokie. So here we basically have to do the similar thing with the previous one where we have to get something into a quadratic form. So if we expand this out, we'll see that there is 4 sine squared x plus, oh, it might actually not be quadratic, it's probably cubic now that I think about it. Well, let's find out. You'll see that there's 4 sine x cosine squared x is equal to 3 plus sine. There we go. And we can do a little fun stuff here because we know that 1 is actually equal to sine square x plus cosine squared x. So we can actually turn this cosine squared into a 1 minus sine squared. So then we'll have 4. Now I'm just going to write sine squared for now, but just assume that sine squared implies that it's of x. 4 sine squared plus 4 times sine times 1 whole. I see the problem. Sine times 1 minus sine squared. Minus sine, because we can bring all the stuff onto the right side or left side. Minus 3 is equal to 0. And this means that we have more sine square terms to, sine terms to group. And we also have this. So we actually have negative 4 sine cubed, because sine times sine squared. And then we have plus 4 sine squared plus 4 sine squared. And then we have plus 4 sine from here and minus sine from here, which makes plus 3 sine. And then minus 3 here, and that's equal to 0. And if we do a little bit of factoring, we can actually see that we can factor out a 4 here. Sorry, not a 4. You can factor out actually a 4 sine. It's a 4 sine? No, it's 4 sine squared. My bad. You can do 4 sine squared. And then you'd have 1. And then that would be minus sine. But if you notice, there's also actually, you can do that here as well. And since the sign is positive and the constant is negative, you'd have to do minus 3. And then you can do a 1 minus sine. That's all equal to 0. Isn't that fun? And you can now factor this to make 4 sine squared minus 3 is, or multiplied by 1 minus sine is equal to 0. So we want to find all values of x that satisfy this equation. So if we go here, we would have that sine is equal to plus or minus root 3 over 2. So this can be achieved because you need 2 separate sets, since the plus and the minus have different cases, at least I think. So sine of something is equal to root 3 over 2, so that would be pi over 3. And sine of something is negative root 3 over 2, that would be negative pi over 3. Yeah, so you need pi over 3 plus, let's see, does it scale with pi or with 2 pi? Well, what's sine of 4 pi over 3? Okay, 4 pi over 3, that's pi plus pi over 3. Sine of 4 pi over 3 is going to be negative sine of pi over 3. So no, you have to go every 2 pi, unfortunately. So we can't mix them into one. Because every pi, it turns to a negative 1. And here is the same, because the fancy property of sine being an odd function. Sine of 2 pi over 3 is indeed positive. So yeah, we can't. And then here you have 1 minus sine is equal to 0, which means that basically sine x is 1, right? So that only happens at pi over 2. But since it says all solutions, you need to add all like infinite multiples of 2 pi that could be added. And this is for n that belongs to, I think it's any integer. That was very bad, but yeah, that's the solution. Or at least what I believe to be the solution. But I'm pretty sure this is the solution. 21. Okay. Two identical spacecraft of mass m are in stable circular orbits around the Earth, one at height radius of Earth and the other at height radius or to radius of Earth above the surface of the Earth. What is the difference in the total energy between the two spacecraft? The radius of the Earth is radius of Earth. Well, yes, okay. So in orbital mechanics, I believe there is a fancy little formula that gives the, what do you call it? Energy of a satellite in orbit, and it's this. This is also equal to negative k because kinetic energy plus, wait, no, it's not this, it's this. Yes, there's no 2 there because actually if you just think about it, it's only kinetic energy plus potential energy, so there should be no 2 in front. And so it's kinetic energy plus potential energy, but this equivalence here is the fancy formula. Basically, it says that the total energy is going to be, yes, it's negative of the kinetic energy. So I'll call K1 as the one that's at the radius E. So the kinetic energy of that is, I believe it's root G mass over, actually no, kinetic energy, or we can just do this. I'm delaying this too long. I'm sorry. Kinetic energy of the first is going to be 1/2 of negative of the potential energy. And the potential energy is GMM over R. So that would just be GMME. And the distance to the center of the Earth. So the distance to the center of the Earth, since it's at a height of RE, is 2RE, because you have to add the extra one from the Earth itself. GM, well, it's negative actually. And then you have to multiply it by a factor of 1/2 due to this. And yes, you get that it's GMM sub E over RE times 1/4. So for sake of not having to write so much, I'm just going to call this quantity L. So GMM over E divided by the radius of the Earth, that's going to be L. And therefore, that means that the energy of the first spacecraft is going to be the negative of that, which is negative L over 4. And so the kinetic energy of the second spacecraft is also going to be, I should probably specify this as U1, the same. It's going to be the potential energy over 2 times the negative, which, or at least this is how I believe it goes. And over, so since this is a distance 2RE above, this is going to be 3 times the radius of the Earth. And there's going to be a 1/2 factor there. Yes, this should be it. And once again, this is actually going to be L over 3, which means the absolute value of the difference in energies is going to be L times, what do we get here? We got -1/6 and -1/4. Oh, that's basically just 1/6 minus 1/4. Put a negative there. That again was supposed to not happen, but it did regardless. That. And 1/4 minus 1/6, or here in this case, it's going to be 4 minus 6, so -2 over 24, so -1/12, and the negative of that is 1/12. So the answer is, I believe, 1/12 of this quantity right here. Yes, this should be the difference in total energy, I believe. Yes. I probably should have derived the kinetic energy using the centripetal motion business, but regardless, this formula is very handy, so it works. And we have an answer. Oh my God, we're not on the last question because I have questions to go back to. Okay. A beam of light in a medium with refractive index n1 is incident at angle θ1 on a slab of material of thickness d with refractive index n2, which is greater than n1, as shown in the figure. The rear surface of the slab is mirrored and is perfectly reflective. To what distance L does the beam transmitted into the slab travel into the slab? Wait, what? I'm sorry. What distance L does the beam transmitted into the slab travel before re-emerging? Express your answer in terms of n1, n2, θ1, and d. N2 is greater than n1, right? I'm not very good at refractive indices, so I'm going to assume that this I think there should be another factor in there. Is it like d sine theta? Well, who knows? I'm not necessarily doing this to be correct. I'm just doing it to do it. So I'll just say d sine theta 2 over, oh, does this actually work? I don't know what distance it travels before going. Actually, the distance shouldn't matter because I think the ratio of the refractive indices is this. Yes, okay. Well, I guess that gives us what we need for theta 2. I think that's theta 2. And we need what distance it travels, right? So we basically need 2 times of this, which would be d over cosine theta 2. Okay, well, let's isolate theta 2 first. Theta 2 is, I think it's gonna work. Okay, well, this is what I think theta 2 is. So theta 2 is, and now I need the cosine of it. D over the cosine, 2 times D over the cosine, right? Cos theta 2. And that's going to be 2D over, okay, cosine of arcsine is root of 1 minus x squared. I'm going to pray this works. Because I don't actually know if it does. This is what I assume this is L. Well, I hope it is, because I am not doing any more. Oh, what are the limiting values of L at large and small theta 1? Well, if theta 1 is small, then we can assume it's 0, which does not work. Actually, no, we can just assuming that this has to be positive, right? Which means 1 minus n2 over n1 squared sine squared theta 1 has to be greater than or equal to 0. Which means basically the absolute value of sine theta needs to be less than n1 over n2 actually. Because if you add this to both sides and you multiply n1 over n2, yeah, and then you take the square root. That's kind of annoying. Let's see, sine theta is positive, is just, yes, it's to be less than this, or if x is less than absolute value of x is greater than the negative of it, greater than or equal to negative, that's n1 over n2. And I suppose that would be what would cause the limiting values of L. Well, when theta 1 is 0, it's just 2D. And when theta 1 is approaching 90, it's just, actually, if it approaches 90, it just blows up to infinity. That makes sense. Sure. Okay. And now consider the case in which light of wavelength. Oh, I need to scroll down to be able to see the problem. I can actually probably clear this considering we've established some stuff. Now consider the case in which light of wavelength in medium 1, lambda 1 is incident normally. For what values of D would light reflected from the two surfaces interfere constructively? Interfere constructively? Okay, so I know that that's supposed to, oh, it has to do with their phases, right? Yeah, okay, I'm gonna be honest, I don't know how to do that. So I'm not going to do it. There's 24. Oh, Jesus Christ. Okay. Hmm. Oh well, I'm not doing this. Or am I? Actually, no, I'll do this. Why not? Yoki. What is the period P? That's a bad letter, but P is going to be 2 pi over omega. And I think the phase shift is all the constant terms. But this is a function of two variables. Hmm. Okay. As if with respect to t, it's lambda or yeah, lambda over v. Hmm. You know what? I'm just gonna say it's lambda over v because I don't want to do any more of this. What total vertical distance does the ship move through a time interval equal to p? Hmm. What if you just hold constant? I don't know. Sketch curves for the ship's kinetic and potential energies as functions of time on the same plot. From t equals 0. Nope, I'm not doing this. Okie dokie, never mind. Yeah, so I only did 22, actually even less than 22 or 23. I didn't do some of the problems that I didn't know how to do. So I only did about, I'll say 16-ish problems. Actually, 16 might be an underestimate, maybe 18. But yeah, I only did around 16 to 18 of the problems. So I guess I was a bit misleading when I said I'd take the whole exam. But regardless, I am not doing this again. This was a very displeasing experience overall. Actually, no, not really. Only the last like two-ish questions were displeasing. Everything else was fine. But that's it